In class last time we solved the problem about the heavy pulley without anything attached to it, and then we solved for the moment of inertia, which I believe was equal 0 point I equals 0.385 kilogram meters squared. Now we are going to make this problem a little bit more challenging, a little bit more interesting, by attaching a bucket to the problem, to the wheel, to the pulley. So now we have, instead of a constant 15 Newton force applied to the cord, we have a bucket of weight 15 newtons. If the weight is 15 newtons, that means that the mass is going to be 153 kilograms. And what we will calculate is the angular acceleration of the pulley and the linear acceleration of the bucket. The frictional force, frictional torque is the same as in the previous problem. So I'm going to scroll down. Let's see what we will do here. We have to remember, since we're given something about the torque and we're looking for the angular acceleration, I alpha is the net torque, so sum of tau, which is going to be equal radius times the force of the cord or the bucket minus the frictional force, frictional torque. All right, so from here, that is our equation. Now from here we we don't know what this force is, Ft, but from the Newton's second law we know that mg minus, if you look at this diagram, minus Ft has to be equal, that's supposed to be T equals, has to be equal ma, right? And from here Ft will be equal mg minus ma, similar to the other Newton law, second Newton law physics. And we also know the tangential acceleration in this case is the only acceleration that is acting on our pulley. So that means that the acceleration has to be equal tangential acceleration, and we know the acceleration is r times alpha from our equations. Now we can substitute that instead of this a. Okay, so f of t is now equal mg minus m, and instead of a we write down r times alpha, and then guess what, this ft is going to plug into here. So we're taking this equation and plugging in here, and now our equation becomes this: I times alpha, which is the total torque, has to be equal r mg minus mr alpha minus the frictional torque. Let's distribute. We get rmg minus mr squared alpha minus frictional torque. We have alpha on the left side of this equation and on the right side of this equation. So when we solve for alpha, we will get mgr, so this little piece, mgr minus the frictional torque over I plus mr squared, because you would have to add this part to the left side, so that's why you will have a plus. All right, and then from here we just plug in our numbers. Alpha is going to be equal 15.0 newtons times g, mg is already the weight, so 15.0 newtons, times the radius, which was the same in the previous example. It was 0.330 meters, minus 1.10 meters times Newton, all over, we get I from the previous example, that was, as I said, 0.385 kilogram times meter squared, plus mass that's calculated here is 1.53 kilogram, and we're multiplying by the radius squared, 0.330 meters squared. If we do our calculations correctly, we're going to get 6.98 radians per second squared, and that is the angular acceleration. And we also need to calculate the linear acceleration of the bucket, which we can calculate from this equation. A is going to be equal r times alpha. So now I'm multiplying my 0.330 meters times 698 radians per second squared, and I'm going to end up with 2.30 meters per second squared.